This page introduces a really interesting concept in processor design, the coprocessor. Think of a coprocessor as a specialized helper for the main CPU. It's designed to handle specific tasks very efficiently, freeing up the main processor to focus on general-purpose work. Historically, on earlier ARM processors, system designers had a lot of flexibility. They could actually design their own custom coprocessors and add them to the ARM core. This was a powerful way to expand the ARM instruction set. For example, if you were building a device that did a lot of a specific type of mathematical calculation, you could create a coprocessor with new instructions just for that task, making your device much faster. However, as ARM processors evolved, this practice was discontinued. Newer processors don't allow you to add your own user-defined coprocessors. Why the change? There are a couple of good reasons. First, it's generally better and more standardized for designers to use what are called memory-mapped peripherals. Instead of a custom coprocessor, you'd have a separate hardware block that you communicate with through memory addresses. This is a cleaner, more modular way of designing a system. Second, creating a coprocessor was actually quite difficult. A coprocessor has to be very tightly integrated with the main processor's core pipeline. That's the sequence of steps the CPU goes through to execute every single instruction. Tying into this pipeline is complex and can introduce all sorts of timing issues. Using memory-mapped peripherals avoids this deep integration, making the whole system design process easier and more reliable. Now, this is a very important point. Even though you can't add your own coprocessors anymore, ARM itself still uses the coprocessor concept for its own internal functions. These aren't extra chips you add. They are standard parts of the processor core. Why does ARM do this? It's a clever way to provide access to essential functions without forcing a specific memory map on system designers. By using the coprocessor instruction space, ARM gives a standard way to talk to these internal units, regardless of where they might be in the system's memory. This slide gives us 3 key examples of these internal coprocessors, which are identified by numbers like CP15, CP14, and so on. First, we have the System Control Coprocessor, CP15. This is probably the most important one. It's like the master control panel for the entire processor. Through CP15, you can configure the processor's system ID, manage the caches, control the Memory Management Unit, PMU, and access other critical settings. Next is the Debug Coprocessor, CP14. As its name implies, this is used for debugging. It provides access to special registers that allow developers to monitor and control the processor's execution, which is essential for finding and fixing bugs in software. Finally, there are CP10 and CP11, which are used for VFP, vector floating point, and neon. These are the specialists for heavy-duty math. VFP handles complex floating point calculations, while neon is an advanced SIMD engine, which stands for Single Instruction, Multiple Data. Neon is fantastic for multimedia applications like video decoding or audio processing because it can perform the same operation on a large set of data all at once. In many modern processors, particularly those based on ARMv6 and the ARMv7-A and our profiles, we find a very useful hardware block called the Performance Monitoring Unit, or PMU. Its job is to help us understand what the processor is doing and how efficiently it's running. Think of it as a sophisticated diagnostic tool or a fitness tracker for the CPU. One of the most important features of the PMU is that it's non-intrusive. What does that mean? It means that when you enable the PMU to collect data, it doesn't slow down the processor or change the timing of its operations. The act of measuring doesn't interfere with what's being measured. This is crucial for getting accurate performance data. So, how do we actually use this PMU? The slide lists 3 ways to access it. The primary and mandatory way is through CP15, the System Control Coprocessor we discussed earlier. You use special instructions to read from and write to the PMU's registers via CP15 to configure it and get the results. There are also two optional methods: a memory-mapped interface, where the PMU registers appear at specific memory addresses, and an external debug interface, which might be used by hardware debugging tools. Now, what information can the PMU actually give us? It provides several key things. First, there's a cycle counter. This is a very basic but essential counter that simply ticks up with every clock cycle of the processor. It's a precise way to measure how much time has passed. Sometimes it includes a divider, for example, counting only every 64th cycle to prevent the counter from overflowing too quickly. More powerfully, the PMU has programmable event counters. These are the real heart of performance analysis. You can program these counters to track specific hardware events. For example, you could configure a counter to count the number of instructions executed, or the number of times the processor missed the cache and had to fetch data from slow main memory, or how many times its branch prediction was wrong. The exact number of these counters and the specific events you can monitor can vary between different ARM cores. So, what happens when a counter gets full? The PMU can be configured to generate an interrupt when one of its counters overflows. This is incredibly useful for profiling. Instead of constantly checking the counter value, your software can just wait for an interrupt, which signals that 1,000,000 cache misses, for example, have occurred. This interrupt signal is an output from the processor core itself, and it needs to be connected to the system's main interrupt controller so that the operating system can handle it. This allows for sophisticated, low-overhead performance monitoring while the system is running.